Hopefully it's a bit warmer for you guys. Okay, so today and next week we talk about isotopes. And I'm going to kick off with radioactive isotopes. Now, radioactive isotopes provide the only quantitative way we have of measuring geological time. We have sort of stratigraphic succession, we can tell younger rocks are on older rocks, there are fossils around, etc., etc. But in terms of absolutely measuring time, radioactive isotopes is the only way we can do it. And I would argue that this has had as profound an impact on human society and the way we view ourselves as the discovery of DNA and how we can use DNA to find our place in the world. I mean, we know from DNA how we're related to other sort of living organisms on the planet, how we relate to one another, to illness and disease and all that sort of thing as well. Now, geological time, the only measure of geological time, provides a huge sort of peg for us to hang our position in the universe on. So, we can measure through human history, through sort of cultural books, we can go back maybe thousands of years. But that really only touches on a fragment of time. We know from radioactive dating that our Earth is 4.5 billion years old, more or less. And so where we sit in that fragment, our lives sit in that fragmentary period, in that huge stretch of time since the Earth was formed, gives a real sort of perspective on where we sit in the world. And so when we talk about things like climate change, we see it in our lifetime. But how does that relate then to the history of the Earth? We're talking about building and destruction of mountain belts. How long does that take? The circulation of the oceans, even something as trivial as evolution of snails. If we can't date it, we cannot study it. And isotopes also allow us to look at the origin of elements in various parts of the Earth. And that can be things as varied as where granites come from, where salts come from in the ocean. So radioisotopes are extremely important. And we'll also look at stable isotopes in this regard as well. So what is radioactivity? I mean, you all have some sort of perceptions of it. You've got the periodic table here, which is made up where the elements are sort of distributed according to increasing atomic number. And that atomic number we see against all the elements is a measure of the number of protons in the nucleus of that element. So if we take, for example, helium, helium-2 is up there. So all helium atoms, by definition, have 2 protons in their nucleus. But some contain an additional neutron, and some contain 2 neutrons. And the mass number, which we put as a superscript in front of the chemical symbol, is the combination of the number of protons plus the number of neutrons. And say every element sits in the periodic table according to the number of protons in its nucleus. So if we take, for example, fluorine out there also sort of down one across from helium. Fluorine is atomic number 9. So all fluorine atoms have 9 protons in their nucleus and 10 neutrons. And there's only one stable isotope of fluorine. So fluorine has a mass number of 19. However, the nucleus of atoms is not always completely stable. Some nuclei undergo spontaneous decay and they emit matter and they emit energy. This is what definition of radioactivity is. And when a radioactive isotope decays, when it undergoes this transformation, it can produce either a stable or another unstable nucleus. And the elements I've put with a red star here are the most important elements in geochemistry that are radioactive. So hydrogen has two stable isotopes, hydrogen 1, hydrogen 2, but also there's a radioactive isotope of hydrogen, hydrogen 3, which is also known as tritium, has a half-life of about 12 years, and it's very useful for dating groundwater. Sorry. And we go along a bit further, beryllium. There's a stable isotope of beryllium, beryllium-9, but there's also a radioactive isotope of beryllium, beryllium-10, which has a half-life of about 1.5 million years, and that turns out to be quite useful for dating some sedimentary process. Carbon, as you know, I'm sure, has two stable isotopes, carbon-12, carbon-13. Carbon-14, radioactive, also known as radiocarbon, has a half-life of roughly 5,500 years. And I'm sure you've all heard of radiocarbon dating. Very useful for dating organic matter. And then we have some of the longer-lived isotopes. So potassium-40, rubidium-87, rhenium-187, samarium-147, uranium-235 and 238, and thorium-232, all have half-lives that are on the order of sort of 1 billion years or so. And they're very useful for dating long-term geological events. Some of these other ones have much shorter half-lives, and we'll come on to those in the second lecture. And these are the sort of the isotopes that are produced by radioactive decay. So we have hydrogen-3, just decays to another isotope of hydrogen. Helium is produced by a lot of radioactive decay, as you will see. Potassium decays to argon. Rubidium decays to strontium. We get rhenium decaying to osmium, and a whole bunch of other isotopes that are produced by radioactive decay. This isn't a complete list, and actually if you look at that geochemist's periodic table that I gave you, we went through in the first lecture, you can actually trace the path of some of these radioactive isotopes. If you look at your periodic table, you'll see you can follow certain isotopes through. So let's have a look at this in a bit more detail. So radioactive decay can occur by quite a few different mechanisms. The most important for geochemistry are electron capture, beta decay, and alpha decay. I'll just go through what these are. So beta decay is where a neutron in the nucleus is converted to a proton and an electron. That electron can't sit in the nucleus, negative charge, everything else in the nucleus is either got a positive charge or neutral, so it gets kicked out. And that has certain energy, and depending on which isotope it is, has a different energy. And it's an electron, and it gets fired out of the nucleus. It's an electron, so it doesn't have a lot of mass to it, and most sort of beta particles will just pass straight through you without doing any harm. If there's a lot of them, then you could be in problem, because there's a lot of them, then one of them is going to do something important. And it's a bit like sort of, if you were standing the other side of the quadrangle and I fired an air gun at you, it would hurt, possibly, it wouldn't do you any major damage in war event, but if I fired a shotgun at you, which is the whole range of sort of air pellet-sized particles, they would potentially cause you some massive harm. So you can be okay with isotopes emitting small numbers from beta decay. You'd probably be okay. You wouldn't want to be close to one which is emitting a lot of So a good example of this will be the decay of rubidium-87 to strontium-87. And so what we see is the number of neutrons in the nucleus goes down by 1, and the number of protons goes up by 1. So we change from a rubidium element to an atom to a strontium atom. So we're changing the element. And so these two elements have different geochemical properties. They lead to a separation of the parent and daughter isotope. So that's an important example of beta decay in geochemistry. Electron capture is effectively the reverse of beta decay. In this case, what happens is the nucleus grabs hold of the innermost electron orbiting the nucleus, and that adds it to a proton, and it converts that proton to a neutron. So best example of this in geochemistry is potassium-40 decaying to argon-40. So number of protons goes down by 1, number of neutrons goes up by 1. Now in the case of electron capture, from sort of theoretical calculations, because we're actually taking something from outside the nucleus, then in the center of extremely massive stars, then with the really intense pressure and really high temperatures, it is possible that that half-life of potassium-40 may change slightly. Whereas for something like beta decay, that half-life is fixed. Now this has been picked up by some sort of creationists who will then claim, well, actually because maybe radioactive half-lives aren't actually fixed, that maybe the whole idea that we can date the Earth, we can date events, is all wrong. Radioactive isotope half-lives can go up and down depending on which deity you believe in. Now, that may be the case in extreme giant stars, but it is absolutely 100% not the case for any type of beta decay, any type of alpha decay, which I'll discuss in a minute, and any kind of electron capture which occurs in a star the size of our sun. So that is a completely bogus argument. And so if you hear it, argue about it. Okay, so our other way of radioactive decay is alpha decay. Alpha decay involves expelling 2 neutrons and 2 protons from the nucleus. And 2 neutrons plus 2 protons equals a helium. I think in your notes I put up, I made a typo and I'll put helium-4 plus, should be helium-2 plus. So 2 protons, 2 neutrons expelled in a single particle from the nucleus. So what we see, number of neutrons go down by 2, number of protons go down by 2. And a good example of that then is the decay of uranium-235 to thorium-231. You can see that the mass number has gone down by 4. Now, helium-4, that's got a significant mass. I mean, it's an electron is tiny and has essentially no significant mass. The helium nucleus has significant mass. So when it gets fired out of a nucleus, and if it's in a crystal lattice, for example, then it will cause damage to the surrounding lattice. And so for those of you geologists, if you looked at a thin section, for example, there's a thin section of biotite, and sometimes you find sort of zircon crystals in biotite. But zircon contains very high concentrations of uranium, so it emits lots of helium atoms during radioactive decay, and these brown sort of circles you see around the zircon where we've had damage to the crystal lattice. Now, because they're sort of quite large, then the helium atom can actually get absorbed by particles in the atmosphere quite quickly. So there was a sort of alpha emitter here, and I'm stood here, I'm probably going to be okay. It's not because essentially those helium atoms that are being fired out are going to be absorbed by the air molecules. However, if I breathe in a radioactive gas, and radon would be an important alpha emitter, if I breathe that in, yes,
Oh, is that why people on planes get quite sick? I've heard stewardesses, they breathe it in and then it can't escape.
no, that's something else, but you know, it's another type of radiation that's more important on planes, and that's cosmic ray radiation, which I might talk about at some point. But if you have breathed in radon gas is an alpha emitter, and if you breathe it in, then obviously you've got that deep in your lungs, and then when it fires out a helium-4, then, okay, you're not taking a crystal lattice, but it can damage your DNA. So for those of you that live, for example, in parts of Cornwall, where the granites contain very high concentrations of uranium, and as we'll see in the second lecture, part of the uranium decay scheme is to form the radioactive isotope of radon. Your houses need to be well ventilated, because if they're not, you have the potential of building up high concentrations of radon. You breathe in radon, it's not very good for you. Okay, so when we've got radioactive decay, over time, the amount of our daughter isotope, which is what the radioactive isotope decays to, will increase. And so if we've got rubidium-87 decaying to strontium-87, the amount of strontium-87 in our system will increase. The amount of our parent isotope, in this case rubidium-87, will decrease. So mathematically, we can write this like this, where the change in the concentration of the parent isotope with time is equal to the amount of the parent isotope that is present times what's called the decay constant, which is given the symbol lambda. And it's a minus because it's obviously getting smaller. So mathematically we should just say minus dN by dt is equal to lambda n. That's all that mathematical expression means. If we integrate that over time, we get this solution here. And this tells us that the number of our parent atoms, isotopes that we have present today is equal to the number we started off with times e to the power of minus lambda t, where lambda is the decay constant and t is time. So this will be, for example, the number of rubidium-87 atoms that are present in the granite we look at today, and let's say that granite is 500 million years old. Then the number of rubidium-87 atoms we see in the granite today is equal to the number that were there when the granite first formed, times e to the power of minus lambda, and I'll tell you what the lambda values are for different isotopes, times t, where t will be 500 million years. Okay, now the half-life of a radioactive isotope, I'm sure you all know this, is the time it takes for half the number of the parent isotopes to decay. And this is related to the decay constant by the half-life is equal to the natural log of 2 divided by lambda. So for rubidium-87, lambda has got a value of 1.42 times 10 to the minus 11 per year. So therefore the half-life of the rubidium-87 is 4.88 times 10 to the 10 years. Now, it's a long-lived isotope. It's not decaying very quickly. Its half-life is 10 times roughly the age of the Earth. Okay, now the number of radiogenic atoms, or daughter atoms that we've produced since the decay, by decay of the parent, since the date of formation of the sample, we can give this symbol D star. That's simply equal to the number of the parent isotope we had at the start, minus the number of the parent isotope that is still present, because that difference is the number that's being converted to the daughter isotope. Now, in most cases, we also have a small amount or some amount of the daughter isotope present in our sample when we first start our radioactive clock ticking. So for example, if we have, again coming back to say granite, and we crystallize a mineral from it that contains rubidium-87, it will start decaying away then in the crystal to form strontium-87. But in that mineral, we're probably some strontium-87 to start. So the amount of our daughter isotope in a particular sample is equal to the amount we started off with plus this amount which is produced by radioactive decay. And this amount that we started off with is called the inherited concentration. So this is the amount we measure today, is the amount we started with, plus the amount produced by radioactive decay. Okay, so we can combine these equations then to get this top one here. The number of daughter atoms equals the number of daughter atoms we started off with, plus the number of the radioactive isotope that was there to start off with, minus the number we got present. Now, we know that, as I just said earlier, that the number of our parent isotope we got present is given by this top expression here, and we can rearrange that equation to say that the number of the parent isotope we started off with, n naught, is going to be equal to n times e to the lambda t. So, just substitute that in to our equation here. Then we can just factorize this expression, and we end up with this form here. That the number of our daughter isotope we measured today is equal to the number we started out with, plus the number of the parent isotope we measured today, times e to the lambda t minus 1. So, if we look at the rubidium-strontium system, the number of our strontium-87 atoms we measure today is equal to the number of strontium-87 atoms in our sample when we start the clock ticking, plus the number of our radioactive rubidium-87 we measure today times e to the lambda t minus 1. Now, it turns out that actually it's much easier to measure ratios of isotopes than it is their absolute abundance. We can actually measure ratios down to sort of 1 part in a million, extremely precisely with modern mass spectrometers. Whereas the absolute concentration is much more difficult to measure, much more imprecise, because you've got errors in sort of weighing things out. Whereas ratios stay constant. Okay, so what we do for the rubidium-strontium system is rather than measuring the absolute abundance of all these individual isotopes, we measure their ratio. And we ratio them to an isotope of strontium, which is not radioactive and is not produced by radioactive decay. So for strontium, this is strontium-86. So this is what we call the basic decay equation for strontium isotopes. And it tells us that the strontium isotope ratio, 87-86 ratio we measure in our sample today, is equal to the ratio that the sample started out with, plus the parent isotope of our reference strontium isotopes times e to the lambda t minus 1. Okay, now we are most interested in solving that equation for t. Right, we know lambda, the decay constant, we can measure that in experiments. So for rubidium, what they did is they took a big vat of very pure rubidium and essentially measure the ingrowth of strontium-87 over time. And so you can measure that, determine the half-life, the decay constant very precisely. Now if we've got a sample, we can measure its strontium isotope ratio today. We can measure the rubidium-strontium ratio today. So we've got an equation with two unknowns. We've got time, which we really want, and we've got the initial strontium isotope ratio. So we need to work out that initial strontium isotope ratio. We'll have some way of accounting for it if we're going to measure time. Now, if we're going to do radioactive dating of an igneous rock, then it only works if the system behaves in a perfect way. And that means that all minerals crystallizing from a magma must have crystallized at the same time. Now, if we're looking at a sort of a granite, let's say, which is 100 million years old, and we look at, some of the crystals formed 50 million years ago and some formed 100 million years ago, then we're going to get a weird age when we start looking at the granite. We also need that rock not to have been altered since it formed. So we know, for example, that rubidium is an alkali element. It's fairly soluble. It's like sodium or potassium. It's fairly soluble in water. So if there had been some hydrothermal fluids flowing through that granite, then they could have mobilized the rubidium. And that's going to mess up our isotope clock. And equally, if that rock has been metamorphosed, it's been heated up by some earth event, some big tectonic event, that's going to mess up our isotope clock. So radioactive dating requires that we understand our system. Okay, assuming that's all working, let's take a case then where we have a granite and we have two minerals. Let's say, for example, we have biotite and we have plagioclase. Now, biotite has potassium as a structural component of the biotite formula, and potassium sits just above rubidium in periodic table. It's also an alkali element, and so rubidium quite likes to follow potassium. We take plagioclase, and plagioclase has calcium as a structural element, and calcium sits just above strontium, and strontium quite likes to follow calcium. It's got very similar geochemical behavior. So when we initially crystallize our plagioclase and biotite from the mold, then the biotite is going to have a high rubidium-strontium ratio, and the plagioclase is going to have a low rubidium-strontium ratio. The strontium that's in that plagioclase and biotite when we start off with is going to have identical strontium isotope ratio. That's one of the requirements for our radioactive clock to work. Okay, so that's how it starts off with, identical strontium isotope ratios, different rubidium-strontium ratios. Now, what happens with time? Okay, so with time then, the rubidium decays, rubidium-87 decays to strontium-87, so this ratio goes down and this ratio goes up for both minerals. The mineral which has the most rubidium-87 within it will show the biggest increase in strontium-87-86 ratios and the biggest decline in its rubidium-strontium ratio. And after time, these points will sit here and here. We can then put a line through those points. And where that line intersects 0 on the x-axis gives us our initial strontium isotope ratio. Think about it, if we had a mineral which didn't have any rubidium in it at all, then its rubidium-strontium ratio would be 0 and its strontium isotope ratio wouldn't have changed.